Hi, welcome to Math Fun. Today, we are going to talk about the harmonic sequence and the Euler constant gamma. So, what is the harmonic sequence? Let's start with a definition. We're going to call it Hn. Hn equal to 1 plus the reciprocal of 2 plus the reciprocal of 3, and you obviously can call the first one the reciprocal of 1, don't you? Plus, continue, obviously plus, until the reciprocal of n. Now, as you can see, each items decrease, and in fact, the reciprocal of n approaches 0 when n approaches infinity. So you may wonder if this sequence converge. Well, many of you probably already know, no, it diverges. So our very first step is to prove that the harmonic sequence, as a matter of fact, diverge. So how can we do that? We're going to write in this way. We're going to copy 1, we're going to copy a half. Now, for a third and a quarter, we're going to combine them. And the next one is 1/5, 1/6, 1/7, and 1/8. We're going to combine them. So you have one number here, have two numbers here, and then you have four numbers. As a matter of fact, you can guess our next item will have 8 number, and that's exactly right. You're going to have from 1/9 plus 1/10 and continue until 1/16, don't you? And then you can just continue that way. So let's see here. We have 1, we have a half. What do we want to do here? Well, what we want to do here is that we're going to combine the two and just call them a quarter each. Okay, now you reduce a third to a quarter, you actually get a smaller number. So in other words, this will be bigger than 1 plus a half plus 2 times a quarter, isn't it? It's a quarter plus, now you have 4 number times 1/8. And the next one, you have 8 numbers times 1/16. And when we do the conversion from here to here, we go to a smaller number. The same here, and we can continue. Isn't that true? Now what do we have here? We have 1 plus a half. Hey, this is a half again. Oh, this is also a half. Oh, that is a half too. How many a half? Infinitely many. So this one diverge. This one approach infinity. And because Hn is bigger than this one, so Hn will approach infinity too. So that's why harmonic sequence diverge. Okay. Now you may say, okay, then if it diverge, can it somehow approach to another number that also diverge? And it might make it a little bit easier to understand and analyze, and maybe use it in a more useful way. The answer is in fact yes. As it turned out, the harmonic sequence would approach another number that diverges to whom? To the natural log of n plus a constant. In other words, the limit when n approaches infinity of Hn minus natural log of n plus a constant together, okay, is 0. Now, in fact, this constant is quite important, so that's why we're going to give it a special name. We call it gamma, and this is the very famous Euler constants. Now, some of you may know E is also called the Euler constant. In this case, it's the base of the natural log. Quite a lot of people do it that way, but other people like to call these ones the Euler constants. Then I prefer this way, as a matter of fact. Okay, so this is what we're going to talk about in our next step. We're going to prove that the Euler constant gamma exists, and that will take quite a lot of work. Okay, so let's do it, and we're going to do it one step after another. By the way, I also have another videos about E in my channel. I would recommend you watching that ones. I put the link in the description of this video also. So let's do it. First, let's prove several lemmas, and every one of them are pretty simple, but when we combine them together, it becomes quite powerful. Our very first lemma is, so let's call it lemma 1, is this. We will have a sequence an equal to 1 plus the reciprocal n to the power of n. We're going to prove that this one is monotone increasing, so it goes up monotonely. And how do we do that? Well, it's not quite difficult, so we're going to do it in this way. We're going to have 1 plus the reciprocal n to the power of n, and we're going to take a n plus 1 root. Okay, and this one equal to 1 times 1 plus the reciprocal n plus times 1 plus the reciprocal n, and how many totally? N totally. Okay, so we have n item in this way, 1 plus the reciprocal n, and we need to take a n plus 1 root. Now this is obviously a geometric means, and they are not the same number because 1 is obviously smaller than 1 plus the reciprocal n. So the geometric mean is smaller than the arithmetic mean. So the arithmetic mean is divided by n plus 1, and then you will have 1 plus, all those ones are the same, and you have n item totally, n times 1 plus the reciprocal n, and that will give you n plus 1. On top of it, you n times 1 is n times the reciprocal n is 1, so you have n plus 1, and then plus the other one out here. That will give you 1 plus n plus 1 reciprocal. Ooh, okay. And remember, we have the power of reciprocal of n plus 1 out there. So let's rewrite it. That will give us 1 plus n reciprocal to the power of n smaller than 1 plus n plus 1 reciprocal, and the sum to the power of n plus 1. Oh, so this is in fact an, and this is an plus 1, isn't it? So that tells you an is always smaller than an plus 1. And so yes, this sequence increase monotonely. So we prove our very first lemma. Now we will do the next lemma, and that one is kind of similar to this. So our L2 out here. In this case, we're going to prove, we will still call it AN, okay? This AN is different from the other one, but let's still call it AN. We will have 1 plus reciprocal n, so quite similar to that one, but instead of have power of n, we're going to have power of n plus 1, and we are going to prove this one decrease monotonely. The proof is basically the same, okay? What we are going to do here though is that we're going to rewrite it, and we're actually going to do it this way. We're going to have n divided by n plus 1, and this is the reciprocal of 1 plus n minus 1 n reciprocal, isn't it? Okay, and we have this one to the power of n plus 1, and then we're going to do the n plus 2 root, and that will equal to 1 times n plus 1 times n over n plus 1 continue plus n plus 1, and how many of them? You have n plus 1 of them, and we have a n plus 2 root. Now the same idea, this will be smaller than, now you need to divide it by n plus 2, and you have 1 plus how many total? N plus 1, so n plus 1 times n over n plus 1, and this one cancel out, isn't that true? So this one equal to n plus 1 n plus 2. So in other words, we prove that n to the n over n plus 1 to the power of n plus 1 smaller than n plus 1 over n plus 2 to the power of n plus 2. And remember, obviously, those are positive numbers. Now let's take a reciprocal. If we take a reciprocal, that means n plus 1 over n, and power of n plus 1 will be bigger now, because you take a reciprocal bigger than n plus 2 over n plus 1 and power of n plus 2, isn't it? And this one equal to what? Well, that one equal to 1 plus the reciprocal n to the power of n plus 1. It's our an here, by the way. And that bigger than 1 plus the reciprocal n plus 1 to the power of n plus 2. This is our an plus 1. Isn't that true? So we prove our lemma 2. We want to prove that this sequence decreasing monotonely. And yes, indeed, we did prove that an bigger than an plus 1. Exactly what we want to prove. So we have two lemma now. Now, from these two, we are going to get our lemma 3. So our lemma 3 is this. L3 is 1 plus the reciprocal n to the power of n was smaller than e. E is the base of the natural log 2.7818, that number, and smaller than 1 plus the reciprocal n to the power of n plus 1. Okay, so how do we prove that? Well, we know E is defined as the limit when n approaches infinity 1 plus the reciprocal n to the power of n. And remember, this one increase, isn't that true? This one increase, and E defined as this series approach infinity, so this one is obviously true. Actually, isn't that right? Because what? Because we can write it down if you want. You can do 1 and it's obviously smaller than 1 n plus 1 to the power of n plus 1, isn't it? And even smaller than the next one, and remember it approaches E. So this is obviously true. Now how about the other one? Well, we have to see this. First of all, we just prove that these portions in lemma 2 that it decreases monotonely, and obviously it bound below because it's obviously bigger than 0, obviously bigger than 1 actually, isn't that true? So that means it has a limit. So it has a limit because that is the monotone conversion theory. When it bound below and it decreases, it will have a limit. So let's call the limit of this item. And we know, like we said just now, the limit is this, okay? Well, this one obviously is the same as this, isn't it? 1 plus reciprocal n to the power of n, and with times just 1 plus the reciprocal of n. Now, this part has a limit. We know that this is E. So this is E, and that one has limit, obviously, that is 1. So in other words, these portions, the limit is also E. But remember, this series decreases monotonely, so it's kind of the opposite of this statement. Now we know E will be smaller than that one. So this is our third lemma that we need for our next step. Now let's have our lemma 4. So L4. L4 is just a extension of L3 as a matter of fact. For this one, we're going to prove that the reciprocal of n plus 1 will be smaller than the natural log of 1 plus n minus the reciprocal of n, and that's smaller than the reciprocal of n. So how do you prove that? Well, we take L3, okay? You remember L3? L3 just now is 1 plus the reciprocal of n to the power of n. That one's smaller than E, isn't it? Let's take natural log on both sides. So that will give you n times natural log of 1 plus the reciprocal of n smaller than 1. Isn't that true? Right, that's it. You just move n to the other side, delete n from here, and that divided by n. Okay, in fact, I can delete in this way. So we prove our second portions. Our lemma 3 also have a second part. The second part is E smaller than 1 plus the reciprocal n to the power of n plus 1. The same idea, we will take a natural log, so that means 1 smaller than the natural log of this one would be equal to 1. So n plus 1 times the natural log of 1 plus the reciprocal of n. And we again rewrite it. So that will give us the natural log of 1 plus the reciprocal of n. Excuse me, will be bigger. This side is bigger than 1 divided by n plus 1. We will move n plus 1 on the other side. So now we prove lemma 4. Okay, so that's proof. Now here is our lemma 5. We will going to prove this. We're going to prove a half plus 1/3 plus plus to the reciprocal of n plus 1. That looks like the harmonic sequence, except that we don't have a 1, isn't it? We're going to prove this one smaller than the natural log of n plus 1, and this one smaller than the harmonic sequence up to n, actually. 1 plus a half plus a third plus continue until the reciprocal n. Okay, so how can we do that? Well, we're going to go from lemma 4. So from lemma 4, just now we have this 1 plus the reciprocal n, right? Which is, by the way, natural log, and we have n plus 1 over n, isn't it? And we prove it that this one smaller than n minus 1. Okay, that one smaller than n minus 1. So from there, what we are going to do here though is that we will do this. We will have the natural log of 2 over 1. In other words, we take n equal to 1. 1 plus 1 is 2. And that will be smaller than the reciprocal n is 1, because n equal to 1. Isn't that true? And we're going to plus another item. We can do the natural log. Now we take n equal to 2. So that would be 3 over 2. And this one will smaller than a half, because n equal to 2 now, reciprocal of 2. And continue until we're going to have the natural log of n plus 1 over n, and continue until that and that smaller than the reciprocal of n. Okay, so now what? Well, it's actually pretty simple, because those are natural log and all of them are positive number, aren't they? They obviously have to be. So the left side equal to natural log 2 over 1 times the second item 3 over 2, and obviously the next one will be 4 over 3, right? Etc. up to n plus 1 over n. And now you can cancel, 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 etc. and cancel that one. Smaller than the right hand side, which is that one. And that is our results. Natural log of n plus 1 smaller than this one, which I'm not going to write, and that is the right hand side that we need to prove for our lemma 5. Okay? And very similarly, we can do the same. Okay, we can do a half plus a third plus continue plus to the power n plus 1 this will be smaller than the natural log of 2 over 1 times 3 over 2, continue, to n plus 1 over n, because this was the left hand side of our lemma 4, which was this part. Remember that what that was? This part is bigger than the reciprocal n plus 1, isn't it? Okay, and now you can cancel those one again, and that will give you exactly the result we are looking for our lemma 5. Okay, so you go from lemma 4, this one use the right half portion, and this one use the left half portion, and we have these ones. And finally, we are going to get our final results. Okay, so let's let xn equal to the harmonic sequence 1 plus a half plus 1/3 plus continue plus 1 over n minus the natural log of n plus 1. Just now I in fact put the natural log of n. In fact the n result is not that big a difference, but anyway, let's put the natural log of n plus 1 actually. So what do we get then? What do we get? Well, remember our lemma 5. These portions actually is bigger than that portion, isn't it? So that means this one is bigger than 0. Okay, so this series is always bigger than 0. At the same time, let's take xn plus 1 minus xn and see what we get. Well, we obviously for xn plus 1, you're going to have 1 plus 2 plus 3. The harmonic sequence go to n plus 1. Okay, so the reciprocal n plus 1 minus natural log of n plus 2, by the way, n minus xn would be that item, and let's write down 1 plus a half plus a third plus until the reciprocal n minus natural log of n plus 1. That obviously equal to, all those one cancel out, don't you? So that equal to n plus 1 minus the natural log of n plus 2 plus the natural log of n plus 1, and that will give you, we can combine the two together, can't you? And I'm going to just directly do that. So I'm going to erase that one, make it easier to do that. So that will give you the natural log of n plus 2 over n plus 1, and that gives you n plus 1 reciprocal minus the natural log of 1 plus the reciprocal of n plus 1, and excuse me, according to our lemma 4, this portion is bigger than that portion. Okay, so what is our lemma 4? Our lemma 4 has the right hand side is the natural log of 1 plus the reciprocal n smaller than the reciprocal n. Wasn't that true? And now it's put n plus 1 as n. You get it? So this one is bigger than 0. Okay, so that is bigger than 0. So that tells you though is that this sequence, as a matter of fact, increase. Okay, it increased monotonely, as a matter of fact. At the same time, let's go to the next page because we're out of space, and we're going to use the other portion of Lemma 5. So what we are going to do here is this. We're going to take xn again, okay, equal to 1 plus a half plus continue until the reciprocal n minus the natural log of n plus 1. Now what do we know about this part? Just now we just proved in Lemma 5 that a half plus a third plus continue until n plus 1 reciprocal smaller than the natural log of n plus 1, isn't it? So we're going to put this one in the place of that one, and this is a smaller number. When we subtract a smaller number, that means we will get a bigger result, isn't it? So that means that we will have to put a smaller size out here, smaller than 1 plus a half until the reciprocal n minus a half plus a third and continue until the reciprocal of n plus 1. Okay, so now we can cancel all those one out. That will give you 1 minus the reciprocal n plus 1, which is obviously smaller than 1. So we prove that xn is bounded above. At the same time, we also just proved that xn increased monotonely. So that's why xn has a limit. That is, it's a limit of xn. And we call this limit gamma. Okay, so the limit is gamma. Now, how big is gamma? Gamma is equal to 0.5772156 etc. It's a rather important constant actually, but it's obviously out of the scope of this video to talk about what it is and how to use it. Now you might guess that gamma may be an irrational number, or it could be a transcendental number. But I have to tell you the truth though. That's not known at all. We don't even know whether gamma is irrational or not. I would think it is. It looks like it. If it is not, well, it will be quite unusual, but we do not know. Maybe you can find out later on. So this is all we have for today. If you like these videos, please like and subscribe. Thank you very much for watching. Bye bye.